Okay, so the last thing we didn't finish up yesterday was the mixture problems. This is going to involve basically two things: making an equation and then plugging it in on the calculator to solve for something. So let's say that you had a solution. Okay, what they're going to do is they'll give you an amount of liquid you have in front of you, and then they're going to give you a percentage. This percentage, it's like a concentration. It's how concentrated the solution is. This particular solution is a 35% concentration of acid. So that means out of the 50 ounces that are in the jar, 35% of the liquid is acid, and maybe the other 65% it's diluted with water or something like that. So if only 35% of the 50 ounces is acid, how would I figure out how much acid is actually in the jar? Yeah?
You do 50 times 0.25.
Right. So you do 50, which is the amount, the total amount you have, times the percentage, and that tells you how much acid is in the jar. Okay. Same idea if you had a test that had 50 questions on it, and you got 35% of the questions right. If you got 35% right out of 50, that means you got 17 and a half questions right on the test. So we're going to actually use that information in our first problem, in the problem for this. So the other thing that we're going to need is how do you find concentration? Well, the way that you find concentration, it's a fraction. And since it's a percentage, there's always a certain number that goes in the bottom when you're finding percents. What do you put in the bottom of a fraction when you're trying to find a percent? I'm thinking of a word. Like you always put the what in the bottom? Yeah?
The denominator.
So yeah, what is the denominator when you're trying to find a percentage? It always represents something specific, yeah? The whole, right? The total. So like if you're trying to find your test grade and you got 13 questions right out of 20, the 20 goes in the bottom because that's the whole, and then the part that you're interested in, 13, goes in the top. Take 13 divided by 20, and that's your test grade. So put the total in the bottom, and then in our case, what we're going to be interested in is the amount of acid. So it's the amount of acid divided by the total. And when you do that, it's not going to give you a percentage. It's going to give you a decimal. This will always be as a decimal. And it'll be a decimal between 0 and 1. 0 representing 0%. 1 would represent 100%. 0.6 would be 60%. Okay, but you're going to get a decimal between 0 and 1 when you do that formula. Okay. So now, let's say that we take our solution that we have. It's 50 ounces, and right now it has 35% acid in the solution. What we're going to do is we're going to pour in 100% pure acid into our mixture to make it stronger. I want to find a formula that will give me the new concentration as I continue to pour in 100% pure acid to the mixture that I already have. So to find a formula for the concentration, we're going to use this. We're going to need a variable because we don't know how much acid we're going to pour in. So the variable that we're going to use is x. That's how much pure acid we're going to pour into the mixture. Okay, so let's see if we can find a formula for the new concentration. Okay, so for the concentration, what's going to go in general? What do you put in the top for this problem? The amount of acid. There's two different sources for that. There's how much acid you started with, and then there's how much you're pouring in. How much acid did we start with already in the mixture.
50 ounces.
That's not how much acid we started with.
35%. Or would it be the 17.5?
It would be 17.5. Okay, that's how much acid is in the 50 ounces. The rest of it, maybe it's just water. Okay, so we're starting with 17.5 ounces of acid. And how much acid am I going to add to that?
Would be X.
X. And since I'm adding that to what I already have, we would put a plus sign. That's how much acid you'll have after you pour in X ounces. What you started with plus what you poured in. Okay. And what, in general, what do you always put in the bottom when you're finding a percentage?
Total.
You put the total. Okay. The total is, well, how much liquid did we start with in our mixture?
50.
Started with 50, and how much liquid did we add to it?
X.
X. So there is a new formula for the concentration. So if you tell me you added 10 ounces of acid, I would take 27.5, divide by 60, and that would be my new concentration. Okay. So let's find a graph of that. Okay, so let's type in, you're going to need parentheses because both the numerator and the denominator have multiple terms. So 17.5 plus x, I'm going to divide by 50 plus x. Okay, so let's think about the window. X is the amount of acid that we pour in. What's the smallest amount of acid that we could add to our mixture if we chose? You could add less than 1.
Like 0.
0. You could choose to leave the mixture the way it is. You don't add anything, and then it stays the same. Now, the most amount of acid that we could add, there's no upper limit on that. That's not what this problem is about. So I would just say, let's go up to 200 ounces, just to get a good picture. Now, Y is going to represent the concentration. What did we say the concentration is always between when you use this formula? 0 and what?
1.
Yes, it's between 0 and 1. So we can put 0 to 1, but we know at a minimum the concentration here can't go below what percent?
30.
What is it?
35.
Yeah, it can't go below 35 because that's what you're starting with. And if you don't do anything to it, it's going to stay the same. The only option you have is to add more acid, which makes it even stronger. Okay. So it's technically not going to go below 0.35, but we could go 0 to 1. That's fine. Okay, so when you hit graph, that's what your concentration looks like as you continue to pour in more acid. Now, what do you notice? As you continue to pour in more acid, the concentration is getting higher. But what do you notice is starting to happen with the concentration? Yep.
It starts to like cap off.
Yeah, it starts to level off because the concentration can't go above what?
30. 100%.
Can't go above 100%. That's impossible. Now, could it ever reach 100%?
Yes.
No. No. Why couldn't it reach 100%? Yeah?
Because it's already been diluted.
Yeah. You're already starting with something that's not a pure solution. So it's almost like if you had a giant bucket, you put 1 drop of black in a bucket that's all white paint. If you put 1 drop of black in it, it doesn't matter how much more white you mix in. It's still not going to ever be white again. It'll get more and more diluted. It might be like 99% and then 1% of the other paint, but it's not going to ever be white again because you mixed in something that wasn't. Does that make sense? Okay. So it'll approach 100%, but it'll never reach it. What they want to know is how much acid do you have to pour into that mixture to raise the concentration to 75%? At least 75%. So what that means is you could pour in a certain amount of acid or more. because they want the concentration 75% or higher. So what do you think I would have to add to my graph to figure out when the concentration is 75%? Yeah?
You think you could add like a line intersecting through 75 and then use the intercept?
So yeah, we're going to add a line and we're going to find an intersect. And where would I put my line?
75.
X equals 75?
Well, x equals would be vertical, so we can't do vertical lines on the calculator. So it is going to be y equals because it's a horizontal. But it's not at 75. That's going to be way off my screen.
Would it be at 7.5?
We'll get 175.
0.75. Because remember, the concentration is always between 0 and 1. So if you want to know 75%, you do 0.75. Okay? And then where they cross, that's the amount of acid that you have to add. So if you pour in 80 ounces into the mixture that you already have, you will get a mixture that is exactly 75%. Okay, so just be careful how you answer it, because they said at least 75%. So what does that mean about how much acid I could pour in? 80 or more. Okay. So how much acid? 80 ounces or more. That or more is important. And the higher you want to raise the concentration above that, the more and more acid you'd have to pour in. Like if you wanted to raise the concentration from like 95% to like 99.9%, you probably have to pour in thousands of ounces. Because once you start getting that high, it's harder to change the concentration because it's leveling off. Okay, but that's the mixture problem we didn't get to. Any questions on that? All right, so the last section we're going to look at this week, we're going to do it over 2 days. So we're going to do, we'll do part 1 today, and then we'll do part 2 tomorrow. And in this section, we're going to focus on drawing or sketching a picture of rational functions. Listen. Now remember, if the numerator and denominator have a common factor, what can that cause to happen? Yeah? You can get a hole in the graph. A hole is basically a part in the graph where it jumps, but you can't see it. Right? On the calculator, if you had a line with a hole in it, it might look just like this. You wouldn't even see it. But the way we would sketch it when we do it is like that. No, the hole's not really that big, but we do it like that so we can see it. So a discontinuity is just a spot where you're drawing your graph, you have to lift up your pencil, put it back down, and then keep drawing. Okay. Vertical asymptotes are also a discontinuity. Like I could draw that, and then I have to lift, come back down, and draw again. The difference is a vertical asymptote is a very obvious discontinuity. You can see it. The hole, you can't see it. That's the difference. Any question on that? Okay, so that's just a reminder of something we mentioned yesterday. So if I were to graph this one, x minus 1 divided by x minus 1, is there a common factor in the top and in the bottom? Yes, there is. So then what is going to happen? Well, let's start with what would make the bottom 0 when x is 1. Because 1 would cause you to divide by 0, one of two things is going to happen. You either get a hole in the graph or you get a vertical asymptote. Which one would this be, hole or asymptote?
Hole.
Hole. Yep. So if we type that in, x minus 1 divided by x minus 1. And we do zoom 6. you're dividing two things that are the same. So it's going to look like it's y equals 1. But we know there's a hole in the graph when x is 1, and that's why it comes up with an error. So that particular one has a hole. I'm not going to graph this one, but if I did, would this graph have a hole in it or a vertical asymptote?
Vertical
Yes.
Or no.
Think about the top just means you have this twice.
Never mind. No, I have a hole because there's like things.
Yeah, there's common factors between the top and the bottom. Yep. So there would be a hole again in this graph, and it would be at what number? It would be at 1. Yep. So these kind of graphs have holes. Now, what if I change this one to x minus, let's do 1.1. Do the numerator and denominator have a common factor now? No, I just messed up the common factor. So 1 still causes you to divide by 0, but now it's going to be very obvious that the two halves of the graph don't connect. Okay? Now you get a vertical asymptote. So you just have to make that small change, and it goes from a hole to an asymptote. So when there is no vertical asymptote, we've been calling it a hole, right? In the graph, what it's really called is a removable discontinuity. And think of the word removable as meaning hidden. Right? You substitute the word hidden, it kind of makes more sense. It's a hidden discontinuity. It's something that if you graph it, you cannot see it on the picture. Even if you keep zooming in, you could zoom in all day, you'll never see it because the hole is infinitely small. It's there, but it's a hole exactly at one value and nothing else. So in that case, we had a hole at 1. Is 0.9999999 okay? Yep. 1.0000001? Yep, that's fine. Just at the number 1, we had a hole. Okay, so any question on the formal name for that? Removable discontinuity. Again, think of the word removable as hidden, and that'll help you remember it's the one you can't see. Removable is hidden, can't see it. Okay, so what we're going to do is in a minute we're going to have a problem like this. I want to talk about polynomials for a second. So we might have done this. If we didn't, well, we should review this just to make sure. So what an end behavior model is, I'm going to abbreviate that as we'll call it EBM. Okay, that's what I'll write from now on, EBM. It's basically used to predict what a graph looks like when you zoom out. So it predicts what a graph looks like when you zoom out. Okay, so it's kind of like it's like a big picture idea, right? It's a simplified version of something that shows you what a graph is going to look like. So let me show you guys an example. Let's take. It's a simpler version of original formula. So again, let's say you had this formula, 2x cubed minus 7x squared minus 8x plus 16. If I asked you to find what's called the E, B, Yeah, so it's like another thing we're gonna find now. Like we find horizontal asymptote, we find vertical asymptotes. We're gonna find something now called an EBM. The EBM in this problem is simply 2x to the third power. The way that you find the EBM is you look at your terms. That's the first term, second term, third term, fourth term. Okay, you look at each term. And all you have to do is write down the one that has the highest exponent. That's it. Okay. So the EBM is the term, not just the exponent. You don't just write down a 3. Yes, the degree of that is 3. But I don't want the degree. I want the entire term. The number, the letter, and the exponent on that letter. So let me show you. Let me show you what happens if you graph the original problem in y1 and you graph the end behavior model in y2. Okay, let's see how they look. So the EBM is supposed to be a simpler version of the original problem. It's not going to look exactly the same, but if you zoom out enough, then it will look the same. Okay. You gotta zoom out. All right, so let's put both of these in. Let's put in 2x to the third minus 7x squared minus 7x squared minus 8x plus 16. And then on y2, we're going to put in 2x cubed. Now I'm going to set a window that's not zoomed out first. And let's see what happens. So let's do a window of -8 to 8. Okay, that's not very zoomed out. And -100 to 100. For this particular graph, that is not zoomed out very far. Okay, so I did -8 to 8 and -100 to 100. I'm going to hit graph. What you're going to see first in blue, that's the original problem. Now what you're going to see in red is supposed to be the simpler looking version. But do they look exactly the same? No, it's because we're not zoomed out. Let's zoom out more. Okay. We know that in the middle here, there's kind of this wave where it goes up and down. Okay. Instead of having our window there, let's set our window from -40 to 40. -40 to 40. And let's set the y values from -10,000 to 10,000. Now I'm zoomed way out. And I want to compare how the original problem and the EBM look this time. I want you to tell me how similar or different you think they look. There's the original problem in blue. And here in red is the EBM. How do they look now?
Very close.
Very close. They're not exact, and they never will be. That's not what the EBM is. It's not an exact picture of the original. But it's supposed to give you a pretty good looking picture of it if you zoom out enough. And if you zoom out even more, we could make these look even more similar. Okay? So that's all that the EBM is. It's a formula that represents generally what the original problem is going to look like on a graph, without all the little details. Okay. Any question on that idea? So that's called an EBM. EBM. Okay. So now, I'm going to write this a little different. Okay. So now, let's do it like this. EBM in rational functions. So what I just showed you is how to find the EBM of a polynomial. Well, now we're going to do it for a rational function. The only difference is a rational function is two polynomials. There's one in the top and one in the bottom. And we're going to do it exactly the same way. Yep, rational functions. So step one, you're going to find the EBM of the top. Step two, find the EBM of the bottom. Step three is you're going to divide the two, and that's the answer. So now, we'll say divide the answer from step one by the answer from step two, and simplify it as much as you can. So that's how you find the EBM in a rational function. I'm going to go back up in 1 second. Okay, let's look at an example. Say we had 8x cubed plus 4x minus 6 over 3x to the fourth minus 5x squared plus 2x minus 12. Okay, so let's start with the top. What is the EBM, or what is the term that basically is going to predict what the top is going to look like? So what's the term in the top that's going to predict what it looks like? 8x to the third. Okay. I'm not saying that this is equal to it. It is not equal to it. It's similar to it. So it's 8x to the third. And what's the term in the bottom that's going to predict what that one looks like? 3x to the fourth. And now we simplify that as much as we can. If you're not sure how to, it might be easier to think of it like this. 8 times x times x times x. 3 times x times x times x. How many x's can I cancel from the top and the bottom at the same time?
3.
I can cancel 3. 3, 3. What does that leave me with in the top?
8 divided by 3.
Leaves me with 8 in the top. And what does it leave me with in the bottom? 3x. That is the EBM for that problem. So that's how you find the EBM of a rational function. And what that means is if you were to graph this, and you were to graph that, and you zoom out really far, they're going to start to look the same, like on the ends of the function. They might not look the same in the middle, and we saw that. Right? One of them had that big wave, and the other one didn't have a wave at all. But if you zoom out enough, they're going to start to look the same over in like this area and over in this area, way on the sides. That's what the EBM is used for. Okay. Any question on that? All right. So let's try finding the EBM, and then we're going to also do horizontal asymptotes. Okay. So EBM. What's the EBM of what's in the top?
2x squared.
2x squared over. What's the EBM of what's in the bottom?
3x cubed.
3x cubed. And without me writing like x, writing it out, anyone think they can simplify it and give me the EBM? Yep.
2 on the top, 3x on the bottom.
2 on the top, 3x on the bottom. There you go. Any question on the EBM? So now, what do you do with that? Well, the EBM is a simpler way to get the horizontal asymptote. We had a problem in the homework last night where we had to use long division, right, to figure out the asymptote. You still have to do long division if you want to know the transformations. Okay, there's no real shortcut with that. But if all you want to know is the horizontal asymptote, you don't have to do long division. Okay, there's an easier way. So to find the horizontal asymptote, all you have to do is find the EBM, and in the EBM, let x approach infinity. That's all you have to do. Take the EBM and let the x get bigger and bigger and bigger in the EBM, and that'll tell you what your horizontal asymptote is. None of this stuff that I just crossed out in red makes any difference with the horizontal asymptote. And the reason it doesn't is because cubing something completely overpowers multiplying something by 2 and adding 1. It's not even close. Like if you take 1,000,000 and you cube it and then triple it, that's going to be way bigger than taking 1,000,000 and doubling it. Cubing is just so much more powerful that this other stuff doesn't even have an effect on the problem. So let's look at the EBM. What's going to happen to the bottom of this fraction as x gets bigger and bigger? Just the bottom.
It'll also get bigger.
It will also get bigger and bigger. Right? So the bottom is going to continue to get bigger and bigger. What's going to happen to the entire fraction if the bottom is getting bigger and bigger?
Gets smaller.
It gets smaller. And it gets so small that it approaches what? It's going to approach almost 0. Yep. So that is your horizontal asymptote. Now, will it ever reach 0? No. It's the same idea as having like that one drop of like green paint in a giant bucket of white paint. You can't make it white again if you put in a drop of green. Right? With here, you're taking a number that's not 0, and I don't care how big of a number you divide it by. If you divide 2 by 1,000,000,000, it's still not 0. 2 divided by 900 billion. No, it's not 0. It's small. But it will never be 0. The only way to get 0 is if the number at the top was a 0. And it's not. It's a 2. It'll never be a 0. It's always a 2. So any question on finding the EBM and then the horizontal asymptote? Okay, let's try this one. What do they want? Do they want horizontal asymptotes? Yeah. Okay. So you can start with that. It's always going to be y equals for the horizontal. All right. What's the EBM of what's in the top? 2x to the fourth. I'm going to do it off to the side, and then I'll put the final answer in the box. Okay. What's the EBM of what's in the bottom?
3x to the 4.
And when you simplify that, what do you get?
2
2 over 3. 2/3. That's your EBM. Okay, now, I'm going to ask you the same question I did about this one. I want you to look at this box, and I want you to tell me what happens to the number in this box as the x continues to get bigger and bigger. Just like we did up here. We looked at the x and looked at what happened as it got bigger and bigger. What happens to the number in this box? Nothing, because there's no x. So so that number is going to basically just stay as what?
2/3.
It's going to stay as 2/3. Because there is no x in that box, as x gets bigger and bigger, it has no effect on the number in that box. So this is when your horizontal asymptote is at 2/3. And if you notice the difference, this one's at 2/3. This one was at 0. It will always be at 0 when that number is higher than that number. Always. Because that's going to cause more x's to be left in the bottom when that number is bigger than that number. When the two numbers are the same, what ends up happening is all the x's cancel out. There are no x's left in the bottom here because they were exactly the same number in the top. When all the x's cancel out, you're going to be left with a horizontal asymptote that's at a number that is not 0. What number is it at? Well, whatever numbers are right there. That's where it'll be. Okay, so any question on that? So that's the kind of problems we're going to focus on when we sketch some graphs in a minute. The number in the top will either be less than the number in the bottom, like this problem, or it'll be equal to the number in the bottom, We are not going to look at what happens when the number in the top is greater than the bottom. Okay, not today. Okay, so we're going to look at cases where the number in the top is either less than the number in the bottom or equal to the number that's in the bottom. Right? And when we're sketching, we're going to do a combination of some things by hand, and we're going to use the calculator to also help us out. So what are some things that are helpful when you're sketching a graph? Well, knowing where it crosses the x and the y-axis, those could be helpful points to graph. Okay, so what we're doing now is we're coming up with a list of different things that are going to help us make a picture of a problem like that. So finding the intercepts. If you don't remember how to do that, the x-intercept is where it crosses the x-axis. The x-intercept always has a y value of 0 because you haven't gone up or down at all. So to find the x-intercept, you fill in 0 for the y value. To find the y-intercept, that would be like up here. When you're on the y-axis, how far left and right have you gone? 0. You don't go left and right at all. So to find the y-intercept, you plug in 0 for the x. X-intercept, plug in 0 for the y. And you'll have a formula you can plug that into. Like that one right there. Okay, another thing that we want to try to find. We want to try to find the vertical asymptotes. Okay, and that's what we practiced yesterday. So that's where the denominator is equal to 0, as long as there's no common factors. Okay, another kind of asymptote we want to find is the horizontal. But to do that, we find the EBM. The reason we find the EBM is because finding the horizontal asymptote of something like this is complicated. We need a simpler version to work with, and that's what the EBM is. It's a simpler version of that. Okay? So we're going to find the simpler version and work with that to get the horizontal asymptote. At that point, that's pretty much what we can do by hand. Now we're going to use the calculator. So I'll just add in. We're going to check what happens when we evaluate the function using the calculator near the asymptote. So let's say the asymptote was 2. I don't want to know what happens at 2. I already know. It's going to be an error. Can't plug in that number. But when I say near 2, I mean let's look at the graph when x is like 1.99. That's pretty close to 2. And let's look at the graph a little bit bigger than 2. 2.001. So when you check what's happening at an asymptote, you have to check both sides. Right? So if 5 was an asymptote, I would check like 4.99. That's just before it. And I'd check like 5.01. That's just after it. And we're going to see what happens. And by check it, I mean you have to take the number 4.99 and you need to fill it in for x. But we can do that fast on the calculator with the table. And that's what we're going to do. That's why I use the calculator. Okay, at this point, we're probably going to have like 6 or 7 points on a graph. That should be enough information to make a picture, but we can always double check it with the graph on the calculator itself. Okay, so let me just check. I think I had 1, 2, 3, 1, 2. I guess maybe I had 2. Unless there's one down here, 3. So if we get through all 3, that's great. If we don't, I at least want to do 2. Because I want to do one where the exponent in the top is smaller than the one in the bottom. And then I want to do one where the exponent in the top is the same as the bottom. Those are the only 2 cases we're doing today. Okay, so let's try to sketch this one. Okay. First thing I would do when I'm trying to sketch that, is I would factor the denominator, because eventually you're going to have to figure out the zeros of the denominator. Okay? So if you factor it, it's going to make it a lot easier. What would be the first letter in each set of parentheses when we factor it? An X. And what about my signs in between? Both positive, both negative, one of each.
Both negative.
Well, if you put negative and negative, when you multiply a negative times a negative,
Yeah.
you'd get a positive.
Negative and positive.
So you need one of each. And now we need two numbers that multiply to give me 6, and they have to subtract to give me 1. I need a 3 and a 2, and
-2 positive.
we do want -3 and +2. We want the bigger number to have the negative, so we get -1 in the middle. Let's check it. X squared, that's good. 2x, what's 2x minus 3x? -x, perfect. Yep, so that is how you factor it. Okay, so now that we've factored it, let's do our vertical asymptotes. How many different numbers make the bottom 0? 2. Are there any common factors between the top and the bottom? No. So then we are going to have 2 vertical asymptotes. What's one of them? 3. And the other one? -2. Okay. Put those on our graph right now. So vertical asymptote at 3 and -2. So dotted lines, that's how we represent asymptotes. Okay, so we've got the vertical asymptotes. That's good. Let's try finding an intercept. Okay, let's do the y-intercept first. So the y-intercept is when you plug in 0 for x. So let's do that off to the side here. So y-intercept. Plug in 0 for x. If you plug in 0 for x, what do you get in the top? -1. And if you plug in 0 for x, what do you get in the bottom? -6. So your y-intercept is at -1 divided by -6. That's +1/6. So it's just a dot that's a little bit above the origin, 1/6. Okay, let's do our x-intercept. The x-intercept is when you plug in 0 for what? For the y. Yep. Okay. There's no y here. There's no letter y. There's something that represents y. I just need to make sure you guys know what that is.
F of X.
Right. So you basically put in the 0 right there. And then you're going to have 0 equals, and you're going to have a fraction. What's the only way that you can divide two things and ever have it equal 0? Yeah?
Numerator is 0.
Right. The only thing that matters is the top has to come out to 0, and that makes the entire fraction come out to 0. What number would make the top 0? 1. And if you plug in 1, do either one of those numbers cause you to divide by 0 if you plug in 1? No. So that's one thing you have to check. Once you find that 1 is what makes the top 0, if you could plug 1 in and it makes the bottom 0 as well, that's a problem. Then we can't use it. But 1 makes the top 0 and it doesn't make the bottom 0. So that's good. So that means my x-intercept is going to be at 1. Right about there. What else? Let's do the EBM. Now, when you do the EBM, make sure you go back and look at the original. Okay, don't look at the factored one. That might confuse you. What's the highest term in the top?
X.
x. That's the highest degree term in the top. X has a degree of 1. The constant right there has a degree of 0 because it doesn't have an x. What's the highest degree term in the bottom?
X squared.
X squared. And what does that simplify to?
X. Oh, 1 over.
1 over x. Okay, so there is your EBM. Now, for the horizontal asymptote, it's y equals, let x get bigger and bigger, and tell me what's going to happen to what's inside that box.
It's gonna get small.
It's going to get smaller, and it's going to get so small that it approaches 0. Yep. And that is your horizontal asymptote. I'm going to do that in green so you can see it. Okay. Now, the last thing we have is check what happens near the asymptotes on your calculator. So let's plug that in on the calculator. I need to type it in. I would type in the original. There's nothing wrong with the factored one, and I did need it. But now that I used it, I'm gonna go back to the original. It's just less parentheses for me to type in. Minus x minus 6. And let's go to our table. And our first vertical asymptote was at 3. That's the one on the right. What's a number that's just, don't do 3, because you're going to get an error. But what's a number that's a little bit smaller than 3, but extremely close to it? Yeah, like 2.99. We're at negative 400. So when x is just before the number 3, we're going way down. And we're going to be going all the way down to what?
Infinity.
Negative infinity. Okay, so I can't go that low on the graph, obviously, but just put a dot like as far down as you can. So just before the number 3, we're way down. Let's check just after the number 3. What would be a number that's just a little bigger than 3? 3.001. We're at 4,000. So we're heading to what?
Infinity.
On that side, we're heading to infinity. So just put a dot as high as you can. Right. And while we're in that section, let's check one more. Let's check like 2 more points. 1, 2, 3. Let's do 4, and let's do 6, just to get 2 more dots over there. 4 and 6. So at 4, I'm at a half. 1, 2, 3, 4. I'm at a half. And when I'm at 6, I'm even lower. I'm at 0.2. So basically right there. Okay, now let's do the same thing for the other asymptote. That other asymptote is negative 2. What's a number that's just to the left of negative 2, closer to me? Negative 2.001. We are heading towards negative infinity. Okay, we're at negative 6,000. So put a dot as far down as you can. Now, let's check what happens just after the asymptote. Okay, we know at the asymptote you're going to get an error, but let's just go a little bit past it. So what's a point that's on the other side, just a little further away from me?
Negative 1.99.
Negative 1.99. Negative 1.99. Doesn't matter, just do it like that. We're heading towards infinity. So put a dot as high as you can. Okay. I'm going to do the same thing. I'm just going to get 2 more dots over in this section. Let's do like negative 1, 2. Let's do negative 3 and negative 5. Doesn't matter. I just need a couple. Negative 3, I'm at negative 2/3. 3, so down a little less than 1. And negative 5, I'm at negative 1/4. 1, 2, 3, 4, 5. So I'm not down quite as far. Okay, so what's going to happen is we have 3 different sections in this graph. The vertical asymptotes can never be crossed. So in this section, you have to connect something that's down here to something that's going to be curving like that. So the way that that's going to happen is it's going to go kind of like that, maybe a little more rounded right there, but that's pretty much that section. The upper right is going to look kind of the same way. It's going to come down, and then all of a sudden, it can't keep going down because it hits that green dotted line. It has to start to curve, kind of like that. And then in the middle, we've got 4 dots. We got 2 kind of near the origin. We've got 1 up high and we've got 1 down low. All 4 of those dots need to be connected. And you have to stay as close as you can to the vertical asymptotes, because that's what they mean. You stay as close as you can. So I want to stay close to it, but I can't keep staying right next to it because I have to start to come down and go through those other 2 points. So it's going to kind of flatten out there a little bit. But I can't keep heading right because I run into another asymptote and I have to start to curve down. So I hit that one down there. And that's a very typical pattern for what these graphs look like. 3 sections, 2 that have kind of curves that are like an L, and 1 in the middle that's more like an S. So let's do zoom 6 and see how we did. I should have been a little bit flatter in the middle than I was maybe, but overall it's a pretty good graph. Any question on that one? So the one, I'm not going to quite get to that one today, but the one that we're going to do next, it's pretty much the same thing, but the exponents are the same. The only difference when the exponents are the same is that the EBM is not going to come out to 0 now. So, the horizontal asymptote. You're going to have the exact same graph, but the horizontal asymptote is going to be shifted up from 0 a little bit. So it just moves everything up. All right, but we'll take a look at one of those tomorrow. All right, so we'll do one of those tomorrow, and then we'll do the last part of 4.2. All right, let me just double check this. So that problem, that's the mixture problem that we didn't do. And then let me just check on 234. 234, 1 through 5, that's finding the domains. You don't have to sketch anything there. 9 and 11, 9, 10, and 11, that's the EBM. So those are pretty quick. 15, finding the vertical, the horizontal asymptotes, and the EBM. So we did that. 17 through 22. 17 to 22 is using your calculator and practicing typing in numbers that get close to a number, kind of like 2.99. Okay, so we don't have to actually sketch anything there. Find a complete graph, domain range asymptotes, end behavior model. We are not going to do 24. Let's just do 23, 25. And then 29 is on the calculator, and 33. So there are a few in there to sketch, like 15. That's a sketch, but we can go over some more sketches tomorrow.